Welcome back to my channel. In this video, we are going to be talking about the power series solution of a differential equation. Okay, and the full topic is special function. Then under special function, we are going to be talking about the power series solution of a differential equation. Okay, now if you can remember that the series expansion of e raised to power x is given as the summation of n starting from 0 to infinity of x raised to power n over n factorial, which means that this is x raised to power 0 over 0 factorial plus x raised to power 1 over 1 factorial plus x raised to power 2 over 2 factorial plus dot dot dot, it continues. And then for exponential negative x is going to be the summation of n starting from 0 to infinity of minus 1 raised to power n. Then I have x raised to power n all over n factorial, which is going to give us alternating signs, which is x raised to power 0 over 0 factorial minus x raised to power 1 over 1 factorial plus x raised to power 2 over 2 factorial minus x raised to power 3 over 3 factorial plus dot dot dot. So the sign are going to be alternating. Okay. Now for a differential equation, maybe a differential equation whereby we have that y prime, what am I saying? Y prime plus y is equal to 0. We are asked to solve this. This is a first order linear differential equation. This is first order linear differential equation. So to do this by either separable method or by linear equation, you know that first order linear equation, this is first order linear equation. So any method you like, but the easiest method is by separating it. Separating this, I'm going to have that dy dx is equal to minus y, right? So therefore 1 over y dy is equal to minus the x. Okay, if I separate them, so I'm going to, if I integrate both sides, I'm going to have that this is ln y is equal to what? Is equal to negative x, right? Negative x plus a constant. So I'm going to have that this is y will now be exponential negative x plus c, which will give us that y is equal to exponential minus x multiplied by exponential c. So y is equal to a exponential minus x. So if you look at this, you will see that your y is equal to a, any constant multiplied by exponential x. We have gotten it as all these things, which is, you know that this one is 1, which is 1 minus x squared over x over 1 factorial plus x squared over 2 factorial minus s cubed over 3 factorial plus dot dot dot. So that is the power series expansion. But this one is solving it with normal differentiation. Then we'll now convert the answer to the series. So that is not what we are going to be looking at. We'll be looking at how to solve it using this power series expansion. Okay. So I just decided to refresh your memory on first order differential equation. So, but let's go into the main thing we have today, which is solving by power series. Okay. Solving by power series, you should know that you should know two things. You should know about ordinary point and singular point. Ordinary or singular point. Singular point of a differential equation. Okay. Now let's have this differential equation. We have a differential equation p naught of y prime prime plus p1 of y prime plus p2 of y is equal to 0 at x equal to a. Now we'll say that x equal to a is an ordinary point of this differential equation if this p of 0 does not vanish. That is, if it is not equal to 0. Please note that all these p0, p1 and p2 are all polynomials of x. They are all polynomials of x. So we should note that x equal to a is a singular point of the above differential equation if p0 of a, that is, if I substitute a into p0 and I'm having that is equal to 0. So if it's equal to 0, it means that it has vanished, and vanishing means that it is a singular point. Otherwise, it's an ordinary point. Otherwise, Otherwise, x equal to a is an ordinary point of the differential equation. So you have known that what? Once you substitute that value, x equal to a, inside this p naught of x. I hope you know that this thing is p naught of x, but I did not put the of x. If you substitute it and then you get equal to 0, you conclude that x equal to a is a singular point. But if you substitute and you did not get equal to 0, you got something that is not equal to 0, then it is an ordinary point. Okay? So another pattern they can ask you this thing is when you have, let me show you. Let me write it very well. P naught of x, y prime prime, plus P1 of x, y prime, plus P2 of x, y is equal to 0. Let's divide through by P naught of x. I'm going to have y prime prime plus P1 of x over P naught of x, y prime, plus P2 of x over P naught of x, y is equal to 0. Okay? And then you should know that when a polynomial divides a polynomial, the answer must be a polynomial. So I'm going to have y prime prime plus, let me call it P in general of x, y plus y prime plus q in general, y is equal to what? 0. Now, if they ask you that if a point is a singular or a regular point, or an ordinary point in this pattern, you should remember that what to make a differential equation to be a singular point is when this man is equal to 0. Okay? So, but if the coefficient is 1 here, that means that same person is at the denominator. And when something is divided by 0, it's going to give us infinity. So, we will conclude that, okay, at the same at point x equal to a. So, we'll conclude that x equal to a is a singular point of the differential equation. Let me call this one equation 2. Let me call it equation 2. And this one, so differential equation 2, if p of x is equal to infinity and q of x is equal to infinity as well. So because the x equal s naught are all under the two of them. So if this and this are all equal to infinity, we say that it is a regular point. And when they are equal to infinity, we call them that they are analytic. Or we say that p of x and the q of x are not analytic. So when they are not analytic, means that they are equal to infinity. Because we cannot get infinity to analyze them. So they are not analytic. You understand? So we say that they are what? They are, then x equal to a, not x equal to 0. X equal to a, any constant at all, is going to be a singular point. Otherwise, it's a regular point. Otherwise, instead of putting otherwise, let me just write it in full. The otherwise I mean is that x equal to a is an ordinary point. Is an ordinary point of the differential equation 2 if p of x is not equal to infinity and the q of x is not equal to infinity. That is, p of x and q of x are analytic. Okay? So if they are analytic, we will now say that x equal to a is what? Is an ordinary point of the differential equation. So we are going to be finding the solution, the power series solution of a differential equation where at a point where is analytic. At a point where it is a singular or a regular. At a singular or regular point. Let me use that word. So we are going to find the power series solution of a differential equation at a singular and an ordinary point. Okay? So let's do the first one at an ordinary point. So you should note, let's have a differential equation. If you have a differential equation like this, okay. So let's have this differential equation. We have a differential equation. Y prime prime plus p of x, y prime plus q of x, y is equal to 0. Now we now say that that if x equal to 0, equal to 0 in particular, if x equal to 0 is an ordinary point of the differential equation, then the solution becomes. I hope you still remember what I mean by ordinary point. That means if I substitute 0 in this differential equation, this p of x is not going to give me infinity, and q of x is not going to give me infinity. So if we substitute it and we did not get infinity, we say that it's an ordinary point. So if it's an ordinary point, the solution becomes y is equal to the summation of k starting from 0 to infinity of ak x raised to power k. This is how the solution will look like. And if you expand this thing, you will see that this is equal to what? A naught, anything raised to power 0 is gone. So plus a1 x1 plus a2 x2 plus dot dot dot. It continues in that manner. Okay? So that is the solution to, this is called the power series solution of this differential equation at x equal to 0 being an ordinary point. Okay? So now let us solve the question so that you understand what I'm saying. If we solve one calculation now, you understand exactly what I'm talking about. Example 1. Example 1. Example 1. We are asked to solve. It says solve in series. Solve in series the equation. Solve in series the equation y prime prime plus x squared y is equal to 0. Okay, solve in series this equal to 0. Now, if you are solving in series, don't forget that y prime prime is the same as saying the squared y over the x squared, and then y prime is the same as what? The y dx. In case they did not write it in prime, they decide to write it this way. That means this question is the same thing as saying the squared y over the x squared plus x squared y is equal to 0. So they are the same thing. Okay. So now, the first thing we are going to check is if x equal to 0 is an ordinary point of this differential equation before we solve. Now, if it's obviously that our p of x here is equal to 0. Yes, because there is no coefficient of p of x, and then our q of x is equal to x squared. Is it not true? Now, at x equal to 0, if I put x equal to 0, if I put 0 here, p of 0 is still 0, right? And the q of 0 is still 0 squared, which is still 0. And 0 is not the same thing as infinity. I told you when it is in this pattern, where there is no coefficient, okay, where the coefficient of y prime prime is 1, then we are considering infinity. But if it is not 1, we are considering its coefficient to be 0. You understand? So what do we mean? Since we did not get infinity, we say that since p of x and q of x are analytic at x equal to 0, then x equal to 0 is an what? Ordinary point. Ordinary point of the differential equation. So it's an ordinary point of the differential equation. So since it's an ordinary point, don't forget how the solution will look like. The solution is going to be y is equal to the summation of what? K starting from 0 to infinity of ak s raised to power k. This is how the solution will look like. So if the solution is this, if this is our y, we have gotten our y, we need our y prime prime. So before we get our y prime prime, we need to get our y prime. And for us to get our y prime will now be to differentiate x. That is multiply by the power and remove 1 from the power. So I have the summation of k starting from 1 now to infinity of k ak x raised to power k minus 1. That is, I multiply by the power, then remove 1 from the power. That is differentiation, because what I'm differentiating is with respect to x. So y prime prime is now the summation of k starting from 2 to infinity of differentiating x again. So multiply by this power and remove 1 from the power. So I'm going to have k into k minus 1 ak x raised to power k minus 2. Okay, so that is how it will now look like. So if we now substitute this one and this one, we did not have this one, so we're going to substitute this one and this one in this equation. Let me call this equation star. We are going to substitute it in equation star. Okay, permit me to clean here because it's very long, so that I'll write it the way it's long. So now, if we substitute, our y prime prime gave us the summation of k starting from 2 to infinity of k into k minus 1 ak x raised to power k minus 2 plus x squared. Our y prime, I'm sorry, our y is the summation of k starting from 0 to infinity of ak x raised to power k is equal to 0. Okay, so let us clear this bracket. If we clear this bracket, we'll now do our last evaluation and then we have gotten the answer. So I have here the summation of k into k minus 1 ak x raised to power k minus 2 plus, now according to indices, x squared is multiplying x raised to power k. So indices say that if the base are the same thing, take one of the base, then add the power. So I'm going to have k plus 2. So if this one is multiplying this one, I'm going to have the summation of what? ak x raised to power what? K plus 2 is equal to 0. So the last thing you are going to do for me is to make the x raised to power this to look alike, so that they will be the same thing. And the only way they will be the same thing is either we make this one to be raised to power k and this one to be raised to power k, or we make this one to look like this one to be k plus 2. And if you want to make this one to be k plus 2, that means we are going to add 4 here. So that is, we already have k minus 2. If we add 4 to it, it's going to be what? K plus 2. Exactly the same thing here. So let's say, for us to do it, we'll now say that anywhere we see k, we'll replace it with what? K plus 4. Okay, so we say put put k to be equal to what? K plus 4 in the first summation. Okay, so this is going to be the summation of k plus 4, because I'm seeing k here, so k plus 4 into k plus 4 minus 1 will give what? K plus 3. Okay, then I'm having a k plus 4, then x raised to power k plus 4 minus 2 will give us k plus 2. Okay, then plus the summation of what? ak x raised to power what? X raised to power k plus 2. Okay, is equal to 0. So we are going to factorize. Permit me to clean the question. Permit me to clean everything here so that I can write above. So if we factorize, they have summation in common. They have x raised to power k plus 2 in common. So if I bring out the summation they have in common, so what is remaining here is what? K plus 4 into k plus 3. Then I have a k plus 4. Then plus, what is remaining here is what? A k, and then they all have x raised to power k plus 2 in common is equal to 0. So that this and this times this will give us the first line. This and this times this will now give us the second line. Now, according to quadratic equation, don't forget that if the multiple of two things is equal to 0, it means that either the first one is 0 or the second one is 0. Don't forget. And then x raised to power something cannot be equal to 0. X raised to power a positive number cannot be equal to 0. So we say that x raised to power k plus 2 is not equal to 0. So if this one is not equal to 0, automatically this one is 0. So automatically k plus 4 into k plus 3 a raised to power a k plus 4 plus a k is equal to 0. So automatically. So if I make a k plus 4 subject of the formula, I'm going to be having that ak plus 4 will now be equal to what? Minus ak over k plus, or minus 1 over. Let me write it that way. minus 1 over k plus 4 into k plus 3. Then I'm having ak. Okay? So now let us find our when k is 1, when k is 2, when k is 3, when k is 0. Now, if we say when k is 0, if k is equal to 0, if k is equal to 0, we now have that a4 is equal to minus 1 over 3 times 4, 12, minus 1 over 12, a0. Okay? When k is 1, we have a5 is equal to minus 1 over 12, sorry, when k is 1, 1 plus this is 5, 1 plus this is 5, 1 plus this is 4. So 5 times 4 is 20. So minus 1 over 20 a1. Okay? So when k is now 2, when k is equal to 2, we are going to have that a6, 2 plus this is 6. a6 is equal to what? Minus 1 over 6 plus 5, 30. So minus 1 over 30 a2. And then our answer is supposed to be only in 0 and 1, 0 and 1. And there is no way we can get a2. There is no way we can get a2 at all. It's not possible. So since it's not possible, we conclude that a2 is equal to 0. So if I put the 0 here, which means that a6 is 0 as well. Okay? So we have that k is equal to what? 3. When k is equal to 3, we have that a7 is equal to minus 1 over 7 times 6 is 42. So I have 42 a3. And then there is no way we can get a3 again in terms of a0 and a1. It's not possible. So therefore, our a3 as well is equal to what? 0 again. So we have, if we put 0 here, we have 0. Okay? So look at what I mean by in terms of. For example, we have that we got a 20, for instance, and 20 is giving us minus 1 over maybe 100 a4. We'll see that this a4 can be written in terms of a. So which will now be minus 1 over 100. This is an example for you to understand what I mean. Multiplied by a4 gave us minus 1 over 12, minus 1 over 12 a0. And then we'll clear the bracket and still get our answer in terms of a0. So your answer must be only in terms of a0 and a1. So if you have gotten this now, your final answer becomes, we know that that y is equal to the summation of k starting from 0 to infinity of ak x raised to power k. So this is equal to a0, our a0 plus a1 x1 plus a2 x2 plus a3 x3 plus a4 x4 plus a5 x5 plus it continues that way. So I'm leaving my a0 because my answer must only be in terms of a0 and a1. So a0 plus a1x plus a2. We couldn't get a2, so that one is 0. We couldn't get a3, that one is 0. So a4, what is our a4? a4 is equal to minus 1 over 12 a0. So we now put it minus 1 over 12 a0. So what of a5? a5 is minus 1 over 20 a1. Minus 1 over 20 a1. What of a6? a6 is 0. a7 is 0. So we can just put plus dot dot dot. It continues in that manner. So this is the solution to this. So thank you very much for watching. I'm going to give you an assignment. You are going to solve it. Then tell me the answer on the comment section using power series expansion. Okay? So the question said, that is question number 2 here. Question number 2 said we should find the power series solution of 1 minus x squared y prime prime minus 2xy prime plus 2y is equal to 0. So first of all, you have to check for me if x equal to 0 is going to be what? What is it called? It's going to be an ordinary point of this equation before you start solving. So obviously it's an ordinary point because this one now has coefficient. So we are considering if I put x equal to 0 here, can it give me 0? If it does not give me 0, then it's an ordinary point. But if it gives you 0, then it's a singular point. So in our next video, we'll now talk about a power series solution of a singular point of a differential equation. Thank you very much and God bless you. But before I conclude, they can ask you a simple question. They can ask you to find the singular point of this differential equation. For us to find the singular point, don't forget that this one must be 0. So say that 1 minus x squared must be equal to 0. So therefore, we have that 1 minus x and 1 plus x is equal to 0, right? Because this can be squared. So that is 1 minus x is equal to 0, or 1 plus x is equal to 0. So therefore, we now have that x is equal to 1, or x is equal to minus 1. X is equal to minus 1. So x is equal to 1 and x is equal to 1 are the singular points of this differential equation. So the ordinary point of this differential equation will now be x not equal to 1 and x not equal to what? Minus 1. So every other point except these two are all ordinary points of this differential equation. So the only singular point of this differential equation is what? X equal to 1 and x equal to minus 1. So that is just how to find ordinary points and singular points of a differential equation. So thank you very much and God bless you. Please like, share, and subscribe. Bye-bye.